Hello everyone, welcome back to Chemical Engineering and Aspen channel. As you know, these days we are focusing on the subject of heat transfer operations. So in this regard, we are bringing the lecture number 6 for our valuable viewers. In the previous lecture, we had studied the thermal conductivity, the introduction of thermal conductivity, the definition, the applications, how to measure the thermal conductivity, and the thermal conductivity trends with respect to temperature for solids, liquids, and gases. In today's lecture, we will solve two numericals related to the thermal conductivity. In the first numerical, we will see how we can measure the thermal conductivity of a material and we will calculate the numerical value of thermal conductivity for the given material. In the second numerical, we will convert the thermal conductivity from one unit to another unit. So this is an important activity for those who are interested in learning the thermal conductivity from the fields of chemical engineering, mechanical engineering, process engineering, and physics as well. So if you have not subscribed to the channel yet, please subscribe to the channel. Please click on the bell icon to get all updates related to this channel. So in numerical number 1, we have to compute or we have to calculate the thermal conductivity of a given material by an experiment. So if you remember previously, we had seen how we can measure the thermal conductivity by insulating the sample for which we need to measure the thermal conductivity and then giving the heat through an electric heater or resistance heater. So this is the same example which we are solving here. A common way of measuring the thermal conductivity of a material is to sandwich an electric thermofoil heater between two identical samples of the material. This is sample number 1, this is sample number 2. Both samples are of the same material and the thickness of these two material is same. The thickness of the resistance heater, including its cover, which is made of thin silicon rubber, is usually less than 0.5 millimeter. This is the information about the resistance heater. A circulating fluid such as tap water keeps the exposed ends of the sample at constant temperature. So this is the cooling fluid which is passed through it to ensure that there is a constant temperature. The lateral surfaces of the sample are well insulated to ensure that heat transfer to the sample is one-dimensional as I have shown you previously. Two thermocouples are embedded into each sample some distance L apart and a differential thermometer reads the temperature drop dt across this distance along each sample. So there is a thermocouple here and a thermocouple here. Both have the same value of L and it measures the temperature difference across this point, this first thermocouple, and the second thermocouple measures across this point. When steady state of conditions are achieved, the total rate of heat transfer through the samples becomes equal to the electric power drawn by the heater, which means that the amount of heat that is transferred from this heater is equal to the heat that is gained by these samples. However, there is only one heater, so half of the heat will be transferred to this sample and half of the heat will be transferred to this sample, and accordingly we will measure the change of temperature for both samples. In a certain experiment, cylindrical samples of diameter 5 centimeter and length 10 centimeter are used. So we have been given the information about the dia and length of both samples, and as I have told you that both samples have same dimensions. Two thermocouples in each sample are placed 3 centimeter apart. So the information about the thermocouples is also provided. After initial transients, the electric heater is observed to drop 0.5, 0.4 amperes at 110 volt. So voltage is given, current is given, and both differential thermometers read a temperature difference of 15 degrees centigrade. So both gives us the information about 15 degrees centigrade delta T value. Determine the thermal conductivity of the sample. So we have been given the information about the delta T, current, voltage, the thickness, the dia, and length. So let's solve the example. First, we will assume the steady state conditions exist during the system. So there is no change with respect to time. There is no heat leak or loss to the environment. That is why we can measure the thermal conductivity. If there is any heat leak or any heat loss, we cannot accurately measure the thermal conductivity. And the apparatus possesses thermal symmetry, means going to the part of solution, the electric power consumed by the resistance heater and converted to heat is WE is equal to voltage into current. So 110 into zero point 0.4 will give an answer of 44 watt. Now this power is transferred equally to both samples. So if we want to calculate for one sample, it will be one half of this power. So it means 22 watt will be transferred to one sample and 22 watt to another sample. And now here is the definition about thermal geometry, that regarding the same temperature difference across the same distance in each sample, that confirms that operators possess thermal symmetry. Now we want to calculate the area, so it is pi d square by 4. We know the dia, which is 5 centimeter or 0.05 meter. So accordingly, we get the value of area as 0.001963 square meter. Now we know this formula Q is equal to K8 dt over L. This is Fourier's law of heat conduction. Rearranging it to get K is equal to QL over 8 dt. Now Q is 22 watt, L is 3 centimeter or 0.03 meter. Area is 0.001963 square meter and delta T is 15 degrees centigrade. So we get the value of K as 22.4 watt per meter per Kelvin. So this is the thermal conductivity of this material, which we have computed numerically. In the previous example, we had seen just a procedure, but here we have solved a real-time problem. So this was our numerical one of today's activity. Going to numerical number 2, which is related to the unit conversion, an engineer who is working on the heat transfer analysis of a brick building in English units needs the thermal conductivity of a brick. But we have the value in SI unit, which is 0.72 watt per meter degree centigrade. Now we need to convert this value from SI units to English units. So we know that 1 watt is equal to 3.41214 BTU per hour, and 1 meter is equal to 3.2808 feet. You see, we know the conversion of watt, we know the conversion of meter. For degree centigrade, it is not that simple. For 1 degree centigrade, it is equal to 1.8 degree Fahrenheit. Accordingly, we will make the conversion. Watt is replaced by BTU per hour, meter is replaced by feet, and degree centigrade is replaced by degree Fahrenheit, and corresponding values are put 3.41214, 3.2808, and 1.8. So accordingly, we get conversion of 1 watt per meter per degree centigrade as 0.5778 BTU per hour per feet per degree Fahrenheit. However, we are given the information that the value is 0.72 while we have calculated for 1. So what we need to do, we need to multiply both sides by 0.72. So accordingly, once we multiply this factor by 0.72, we get an answer of 0.42 BTU per hour per feet degree Fahrenheit. So this is the conversion of the thermal conductivity from SI units to the English units. This was the second activity or second numerical from our today's lecture. So this was about our today's lecture, that we have solved both numericals, and I hope you have understood all the aspects of this lecture. If you have any queries, feedback, suggestion, please provide it in the comment box and I would be happy to answer. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.